so much. Thank you so much for the invitation. This is a lovely workshop, and I've loved the schedule with so much time with other collaborators. Anyway, and thanks so much for the invitation to speak. I'm going to talk today about work on topological holography for bulk boundary topological order. It's based on two papers. One's with Corey Jones, Peter Naaijkens, and my student Daniel Wallick, who will be on the job market this fall. I recommend him. That was from 2020. And one is a paper that appeared last week with Corey and Peter, a follow-up that talks about introduces topological boundaries into the story. So today the object of study, so this is motivated by studying topologically ordered systems in the infinite volume using operator algebras, but from a quantum information perspective. That's the idea. So the idea is we're going to start thinking about an abstract quantum spin system. So this is going to be some lattice, which I'm just going to draw as some kind of Z2 lattice, but it can be in any dimension. It doesn't really matter. Draw something like this. Okay. And ordinarily, if you're thinking about a quantum spin system, you would put some kind of qubit on every site or something like this. But we don't quite need that. What we're going to do is for every rectangle, and the choice to work with rectangles is merely for convenience. You can work with whatever shape region you want, but it's easy if you work with rectangles. So for every rectangle, which you're going to call lambda, I have some algebra, some C-star algebra of lambda. And usually it's going to be 5-dimensional, but it doesn't need to be. So in terms of what it makes an abstract quantum spin system, so each A of lambda gets a C-star algebra. So you need the following properties. I have the empty rectangle that just gets the complex numbers. If lambda is contained in delta, then A of lambda is a subalgebra of A of delta. And really, all of these things are living inside some quasi-local algebra, which is the direct limit of all of these. So that could be an axiom, or it could just be the way my definitions. I have a single C-star algebra. I have a bunch of subalgebras. The inclusion works well. And then also, if I have two disjoint rectangles, that implies that these things commute. So here we go on the left there. Okay, so that's the definition of an abstract quantum spin system, and we're going to see many of these things, including real quantum spin systems. Yeah.
Are they finite dimensional or finite? Unfinite rectangle.
It doesn't have to be, but you can. The examples we'll talk about today will. But you could, in principle, you might say, well, what I'm going to do today is really capturing community projector models. If I wanted to try to capture models that weren't community projector, then I might want to lift that finite dimensionality assumption. Okay, great. So the next thing, great. So the next idea is that of a net of projections. And this makes connections with Emil's talk. Okay, so with Emil's talk, his projections, net of projections increased. Ours is going to decrease, so it's just take a 1 minus. Okay, so he was talking about open projections, we're talking about closed projections. So that is, I have p lambda and a lambda for every rectangle, and they satisfy that if lambda is contained in delta, p delta is smaller than p lambda. So this is the usual wording of projections. So this is the opposite of what we're talking about. You can take a limit in a double dual as you were doing, but we're not going to work with double dual. We'll just work with these projections. Okay, great. So these are going to be my example boards. These are going to be like the definition boards. So it's going to look weird when I'm like passing through different boards and erasing different things at weird times. I'll flood it through. If I can pull it off, it'll be excellent. But
so look at like so the resulting space have a lower dimension.
That's correct. It's a subspace. That's right. So this just means the image of, if it were a Hilbert image of a Hilbert space, everything's acting on a Hilbert space, which you can think of it that way. This subspace is contained in that.
So down on the left, you mean that if the intersection is empty, then the commutator is.
Yes. If this is empty, well, if the intersection is empty, then they can. Okay, but it doesn't mean that it's tensor products, right? So that's important. Okay, examples. And it's important that we all, I'm gonna take Agnes's lead here, we're gonna do Torah code, right? We all understand Torah code. So let us do that. In this case, the lattice is not, it's not a Z2 lattice, it's an edge lattice, but you can just turn your head 45 degrees and then it's again a Z2 lattice. But again, this is really robust to the geometry, it doesn't really matter. So here I have a qubit on every edge. For every star S, I get an operator AS, which is, I'm going to use the convention where I put Pauli's V's on every edge. There's another convention you can choose, it doesn't really matter. Here, these are my BPs. This is where I put Pauli X on every edge here. So this is a quantum space system, and I owe you a projection. In this case, P lambda is by definition the product of I plus AS on 2, where S is contained in lambda, times the product of I plus BP on 2, where P is contained in lambda. Okay, so this is just the projection to the local ground state subspace.
I'm sorry. So when you said we should turn our heads 45 degrees, do you mean the rectangles are now also tilted 45 degrees?
Yeah, everything is, yeah, if
Okay.
you just look this way, then
Okay,
you'll
fine.
actually get
Okay.
a Z, like a,
Okay.
so it's all right. But yeah, that works in 2 dimensions, but anyway, that's just a little trick there. Okay, so now I can talk about our axioms here. So this first paper gave axioms, local topological order axioms. So really inspired by Rodney, Hastings, and Naaijkens. Work from 10 and their TQO axioms. We have these things called local topological order axioms. So it's you take what they do and then you want to do it locally instead of, they're working on a finite system, so everything is kind of local. But for us, we're working in infinite volume, but we're only looking locally. So LTO1 says, if lambda is, and here's a special symbol that I'm going to have to define. Lambda is, this is strictly surrounded by delta. So what does that mean? It means this is lambda, this is delta, and then I really want it to be enough on every side. So really it's at least S. So greater than or equal to S here, greater than or equal to S here, etc. So delta has to surround lambda by enough. Then, if I compress the local algebra for lambda by P delta, I just get the scalars times P delta. This here, this is an error correction property. Namely, if you know about the Naaijkens theorem, it means that there's a quantum error correction protocol for local errors in this local algebra using this local code subspace. I can correct for local errors via a local code subspace. Yes.
So in this model, this projection P lambda is construct from the commuting projectors.
That's right.
And we satisfy that condition. But if you construct with a non-commuting projector, whether or not axiom still hold?
That's a good question.
Yeah. So what the question whether we want
All the-
how do you allow
That's right.
non-commuting projector?
That's a good question. So all the commuting projector models that we know and love, they satisfy this.
Yeah.
And so Torah code is one example. Levin-Wen, I'm going to do Levin-Wen after I've done Torah code. I'll do Levin-Wen, and we'll talk about that. And that's kind of crucial to the story today. We expect that this probably means your commuting projector. Okay, especially if the local algebras are finite dimensional. Yes.
In definition of P lambda, you impose not that S is in lambda, but that all the bonds in
The whole S is contained in lambda. That's
contain,
correct.
then do we need that S condition over there? I mean, this
These are different
thickness.
S's.
thickness,
Different S's.
but you still need that one, even if you contain the bonds.
For this, S is 2. So you need to make sure that you, well, it depends how you measure distance, but like you just need a big enough rectangle. Big,
Yeah, so
just make it big. It's fine.
nice.
More questions? happy to answer questions at any time. So, back to, yeah, so anyway, this is an error correction. It also gives you a canonical state. Canonical pure state. And how does that work? Basically, if x is in a of lambda, then I just compress by some p delta. This defines the state. And it's independent of the lambda, where x is in a of lambda, and independent of delta big enough. So you just show that this is well defined, but this is a pure state. Okay. And if this is coming in this way from these local ground state subspaces of a commuting projector local Hamiltonian, then and everything's translation invariant, this is the unique ground state. Okay, so this has been proven in this first paper here. Right. So the example, back to our example, this satisfies LTO1. And to see this, you follow the following steps. Okay, so the first is you can assume some x here, so x is going to be in a lambda, x is a polytensor. Because, well, a of lambda here in this case is just, I didn't tell you what a of lambda was. It's just the big tensor product over vertices in lambda of copies of M2C. Right, it's just on a spin system. The polytensors span the local algebras, so I can assume x is a polytensor. Two polytensors either commute or anti-commute. All right, that's just a fact. Great. 3, if x anti-commutes, say, if x, let's anti-commutes is fancy races here. If it anti-commutes some AS for some S contained in delta, all right, if it anti-commutes here, then what I do is I look at P delta, X P delta. This P delta absorbs every AS term, and it absorbs every BP term, right? Because this community projector model, this term absorbs AS. So therefore P lambda or P delta absorbs AS, so I can create it for free. Since it anti-commutes, I now move it to the other side at the cost of a -1. And I reabsorb it. So it tells me it has to be 0. Okay. So that's step 3, and then step 4. If x actually commutes with every S and P contained in delta, then x is it's a multiple, really a scalar, times a product of AS terms and BP terms for S and P contained in lambda. And this step here is due to Aleki, Penneys, and Morodecki in 07. Okay, so this is a nice algorithm. It's a nice exercise. If you lose the thread today, you can try to prove that. It's a wonderful little thing to prove. I don't want to ruin it for you. It's lovely. Okay, so that's LTO1. Fabulous. Great. So, yes.
This is actually very nice. In some of the works, they use periodic boundary conditions, but I think you want to stay away from periodic boundary.
We're just working in infinite volume because later we're gonna take a physical boundary that's going to be something infinite, and we're just about to get there right now. So that's LTO1. This is really, basically in Rodney Hastings and Balakis. So what do we do in this paper that's interesting? Again, I'm going to start erasing in weird ways, so bear with me. All right, we're going to erase here. This is LTO1. We're going to make LTO2 now. So LTO2. I'm gonna basically give you the idea of what LTO2 is. Really, we have LTO2, 3, and 4 in order to make this precise, but I'm gonna give you the basic idea of what 2, 3, and 4 do. So if lambda is, and now I'm gonna do, it's a different kind of containment here. It's not this strictly contained in, so I owe you a definition there. This is what lambda looks like, but now on 3 sides, I have that strict containment. But on one side, it overlaps. Okay, this intersection I'm going to call I when the boundary of lambda and delta intersect. So this is really making connection with work of Wen and collaborators on their patch operators. That's what this is going to motivate. So the idea is if I have this type of containment where again, this is at least S on all 3 sides except for that one, there exists an algebra, B of I, supported in lambda near I. So this I is kind of fuzzy. It's just fuzzy, right? So it's going to be right up there near I, not exactly on I, such that if I compress A of lambda by P delta, I'll get P of I times P delta. So B of I is now playing the role of the scalars from LTO1. The way you can think about this is that was an error correction thing that allows you to say those, that allows you to correct errors. Now what this is saying is all those errors, they kind of coalesce in that boundary.
This is, you said it exists. Is this data or is this property?
It's actually going to be property. I didn't tell you what 2, 3, and 4 were. This algebra supported near I can be, it can be chosen in a minimal kind of way. It's a prescription, it's a construction, it's a thing that exists from the real axioms that I'm not telling.
Okay.
So the real axioms aren't hard, I'm just doing this for convenience.
So I look in those axioms, I run some recipe, and the actual axiom is that recipe compiles.
That's correct. And it's independent of lambda and delta beyond the fact that their intersection is I. So lambda could go deeper, but then delta gets like way bigger, but you'll still get the same algebra. So it's all these axioms are there to make it well-defined, to make this construction well-defined, but it's really just as soon as I do an example, you'll see immediately, that's what it is.
And you said this is in any dimension, so I'm supposed to read this as like, I have a flat sheet that they're meeting along, or what is the?
So in 2 dimensions, it looks like an interval. In 3 dimensions, it'll look like a rectangle. It's just a codimension 1 rectangle. Okay. And we're going to do an example. We'll do walk along, hopefully by the end, and there we'll get interesting things happening. Okay, so what does this allow you to do? This suggests that we should do the following thing. I'm going to take my quantum spin system and I'm going to make a physical cut, a physical boundary now. I'm going to draw it wiggly for physical boundary because I really think I'm doing something kind of cutting along here and it's physical. Physics is fun. All right, I like that joke. Or okay, so physical boundary. Okay, so I make a cut and I choose a half space H. Okay, so this is a half space, and I can look at A of what I get. I get a quantum channel now, rather than state. And it goes from the half space algebra down to B, which is this injective limit of these algebras along that cut. So I'm taking intervals as they get bigger and bigger and bigger. That gives me an inductive limit Caesar algebra. Some abstract quantum spin chain. Yeah, but it's not a quantum spin chain now. It's very far from being a UHF algebra. So I get this quantum channel, and it's defined by P delta X P delta is P of X P delta. Okay, so it's really, and this looks very pleasing from a subfactor perspective. So I originally started in subfactor theory, so seeing exactly this kind of projections implementing this quantum channel from subfactor. Subfactor theory is going to play an important part in how we analyze these things. All right. The other thing that we get here, now that we have this boundary algebra, is now we can look at Corey-Jones DHR bimodules. For me, these conjecturally, but in every example we know about, they describe the bulk topological order of the system. And so what that means is the DHR bimodules forms a braided W star tensor category. And I probably won't say too much about what it is. The idea is just you're looking at okay, they're Hilbert C star bimodules. Which have FGP bases localized in any large enough interval that we want. Okay. That's basically the idea. If you want to learn more about it, I'll be here all day. Chad, what's up?
Yeah, just you know, in the operator algebra, there are two flavors. One is you don't have representation, don't have purpose, you just some positive map omega.
Okay.
Whether without representation, this DHR bimodule can already be defined. So you don't need a representation.
So there is no
to get this.
There is no representation that you need to define this, right? We have a quantum spin system. We make some physical cut. We're looking at this net of projections. Out pops this algebra, and this is just a definition. It's like literally a full subcategory of all BB bimodules.
I see.
It's not. It's not.
But in quantum stream model, that's a particular representation. But in the mathematics side, you don't need to specify any representation. You already can define the DHR bimodule.
Yeah, the DHR bimodule exists for any 1D abstract quantum spin shape. That's right. It's just a definition.
Constructed entirely from the E of X.
Okay.
Daniel?
So just I'm a little confused why it's W star because you filled out a C star correspondence.
You're right. I'm going to replace W star with C star. Good job. Thank you, Daniel. I like W star, right? That's fine. Because everything really, the ones that we know and love, they're finally semi-simple. So I tripped myself up. Okay. So-
Dave, okay. So when you talk about physical boundary, are you taking the same Hamiltonian and just make a physical cut, or
That's
are
right.
you creating a topological?
That's right. Let me do an example and it'll clear it all up for you.
I see. And in your example, will you explain the quantum channel?
In my example, will I not exactly, but it's basically the algorithm here. You can push things into the boundary and it's basic. Now, one thing that's important to consider is if X is actually supported away, then it's actually going to go, it's just be a scalar. So it's only going to be interesting for things that are really supported near the boundary that are touching. Okay, so let's do the example here for the Tor code. So again, we have this. I'll just draw another thing. All right, so I've got yellow here. It's going to look like something like that. Orange looks something. It's going to be large, something like that. It's going to intersect here. Again, the last time I gave this talk, it wasn't quite clear to everybody. This is like a really large lattice. It's infinite. Okay, so when I'm drawing it, it just ends here for the fact that I don't want to be drawing lines forever. But it's there. And so now I have this intersection part, which is here. In this case, it looks like these edges here that are closest to that part, okay, call that I. And B of I, in this case, it's generated by terms that look like partial Plaquette operators and partial star operators that are confined to this area. Okay, so it's like take all the parts of your interactions that didn't quite fit, and that's what generates the boundary. Okay, so Bowen, does that help kind of?
Yeah.
Okay, so that's what the boundary algebra looks like.
But
And-
do you have the star operator, which is like a T, here, just draw one line to Z.
There's one Z because, right, it would be it would be part of a star, which isn't contained all the way.
Okay, yeah.
Yeah, that's right. Because the star down here is fully contained in lambda. But this one is, this is what survives.
Okay.
And so actually you can describe this in terms of the operators that appear in transverse field easing.
Yeah.
You can just kind of ignore this bottom part and now it's x, x, and z, which we know and love. And it really, you can connect this, you can describe this using fusion categories. Namely either filled Z mod 2 or rect Z mod 2. I don't remember which one it is, but they're the same as fusion categories, but there's a difference when I replace Z mod 2 with some other group. And it depends on whether I took a smooth cut or a rough cut. And so it's one or the other. And so what happens here is that DHR, in this case, is, I guess it's the center, which I'll just write, it's the double of Z mod. Okay. So that's what I get. So I'm recovering the DHR bimodules describe the bulk topological order. And one can think about this kind of heuristically as if I have a string operator that kind of comes in from infinity and kind of lands on the boundary, I can build a DHR bimodule for those, and those are all the DHR modules.
So this one would be like a trivial module, where you have string operator that would be non-trivial module or something like that.
That's right, string operator in there, then I'll have the non-trivial module. That's right.
Thank you.
Okay, so that's LTO1, LTO2, the basic example of Tor code. Yes.
If you do different cuts, you're gonna get different BI, different.
That's great. So if you assume some kind of translation invariance here, then BI works. You might be worried, oh, if I took a cut and I chose a different half plane, that could correspond to taking an algebra or its opposite algebra. So I could get either C or its opposite. But the center of a fusion category also relied on the Z mod. It was a Z mod 2 Forza conventions there, so that's not something to worry about. Potentially, you might, if you could say cut this way or cut that way and maybe get different things, but we don't have examples of that.
But is it easy to see why the DHR bimodule correspond to different cut? They are the same. You do this cut. If you don't have translation variance.
If I don't have translation variance, there's not much I know how to say. So
They might be different.
they could be. They could be. That's right. But we're really approaching this from a quantum information perspective, and so we want some like quantum code here. And so these are, it's not it shouldn't be really a surprise at working it. You're getting out what you're putting in.
But since you want to extract the topological order out of it,
Yeah.
so you want not
That's right.
to be dependent.
So what I think should be the case is, I'm going to speculate, these DHR bimodules should be the same as the super selection theory of the cone algebras. And basically, if I look at a cone algebra and kind of project it to the local ground state subspace for that cone, take the limit of the projector and like the double dual. And if I were to say compressed by that, then I should get the boundary algebra along cone. And so they'll be Morita equivalent kind of as algebras, and therefore have the same whole bimodule space. And then you just have to say what localizable and transportable means, and hopefully those aligns with DHR bimodules, but there's a lot that you have to, there's a lot of hoops to jump through to make it all work. I'm thinking about it.
I think maybe they are translation related and be gathered by local unitary. Hopefully that's kind of isomorphism.
Yeah.
Let's hope.
Yeah, hopefully. That's a great question. But thank you for the questions, and you've delayed me long enough that I can just erase what I just wrote down and write up a new example while leaving all of this on board. So let's do another example. A little more involved. This one we'll do Levin-Wen now. So Levin-Wen looks a little more to me like a Z2 lattice. Okay, so what is this? This is my lattice. What does that mean? So each space here, this is N in C, so C is a UFC, unitary fusion category. This is, I tensor this certain object, X twice, and I look at N. X is the direct sum over the simple objects in my unitary fusion category of the simples, okay? And I just take that endomorphism space, and it's a Hilbert space using the canonical spherical trace for my unitary fusion category. If you're a physicist, you should think of plus in this way, Okay, so here I've got I, here I have J, but I'm already enforcing that in this hexagonal lattice that these middle thing matches, right? So just using semi-simplicity, that moves it this way. I have all the labels that appear here, labels, 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 and then so I'm just pick a basis of tridimensional vertices, but I'm already making the middle thing match. Okay, so that's the Hilbert space. Great. I have two types of terms. Can't remember which colors I used, so it doesn't really matter. Okay, so I think this is right actually. AS just glues the edges. Okay, so it takes something here and here and just glues them together. Just composes. All right. And then BP is the usual Ken operator. And how does that work? Well, once I am in the image of the AS, then I can think of it as having a puncture here in the middle. And then I have a loop here for every simple object C that kind of you have to push it into these spaces and resolve it, even though it's a tensor product. This would be BPC, and then BP is 1 over the global dimension of the category, the sum over my simples of DC times BPC. And this is a screening operator, and it implements the gluing in of two cells. Okay, so it allows for basically the image now. P lambda again is basically it's the projection to the local ground state space. In fact, the image of P lambda is isomorphic to what we call the Skane module for C. On the disk, with the boundary points labeled by S. So what does that look like? I've got a bunch of boundary points here, all labeled by X, etc. And so the image of P lambda is Hom C from 1 to X to the tensor boundary of lambda. Okay, so you just do that, and it's a pivotal category, so really spherical. So it doesn't matter if I put all the X's to one side. It didn't really matter. So that's what the image here looks like. I think, yeah, anyway, this is the Skane theoretic description of Levin-Wen. And so then the LTO1 axiom was originally proved by Chu and Wang in 2020 for the Levin-Wen models. And they use kind of this TQFT type approach, type argument. It's fairly complicated. We give another one, new argument, in this first paper up here, 2307, whatever, using Skane modules. And our proof is extremely short using the Skane module. It basically just uses that the Skane module is an irreducible representation of the tube algebra, or something array equivalent to the tube algebra. So think about a tube algebra that's acting around the outside, but it's irreducible. And because it's irreducible, that's what allows when you compress by these p deltas, you just get a scalar. It's that irreducibility because it's going to be in the commutant of a irreducible representation, therefore scalar. Okay, that's the basic idea about how that works. And we prove LTO2. Again, this is in 2307, whatever. Again, using Skane theoretic, Skane module techniques. And there, something really interesting happens. So again, we had got some rectangle here like this. In this case, you don't really need, you only need S is 1 in this case. I in this case is just the 3 sites here along the boundary, 1, 2, 3. You can think about that as everything is in this image of the ground state. So really you can think of this as connected. And then in this case, B of I is isomorphic to end in C of x to the what I'm going to call x tensor I. So the idea is that these boundary error operators, they correspond to gluing a morphism from the category here on this side. All right. So it looks like, if I'm thinking about what this boundary algebra looks like, I've got a Z lattice. So and then if I have I, which is some integral on that lattice, then B of I looks like morphisms from my category that kind of live over those sites. Here I'm using the graphical calculus for unitary fusion categories. And they include into larger ones just by tensoring with identity strands, okay? And this is what's called the module, the fusion spin chain. For C and X. X is what's called a strong tensor generator, and so we get these fusion spin chains, which Corey studied extensively in the DHR bimodules, the paper which he invented DHR bimodules, and DHR of this fusion spin chain is of course the Drinfeld center. That's what you get. So again, the DHR theory, the DHR boundary, DHR bimodules of the boundary algebra are capturing the bulk topological order. Okay, great. That's Levin-Wen. All right, so that's basically bringing us up through 2307. Again, maybe one last remark here. Well, an interesting thing we found, it's not related to today's story, but if you look at the cone algebras in this version of Levin-Wen, the cone algebras can be type 2 or type 3 factors, depending on the actual unitary fusion category you started with. If it's pointed, you get type 2. If it's not pointed, you get type 3. And this is interesting from a quantum information perspective because you can build what are called universal embezzlers when you have type 3 cone algebras. So that was kind of a surprise that we could get things of either type. Okay.
How about this? If the quantum dimension of X is integral or weak integral, whether there's something about this, what type algebra?
So if C is pointed, then X is of course integral, but you can have a non-pointed category where the dimension of X is still integral. Just take rep G.
Yes, that's right.
Yeah.
But whether this will be still what's the type?
It'll be type 3 as soon as you have an object whose quantum dimension is not 1.
Oh, I see.
You get a type 3 algebra.
But
Right.
you should, but with the caveat that in the Tye's quantum double models, you
Yes.
still get type 2 because those are not actually Levin-Wen models.
That's right. The Tye's quantum double model is not a Levin-Wen model. It depends which cut you take, whether you're thinking about rep G or hill G. And there, the object isn't this X sum of simples, it's the regular element from rep G. So you can't make a regular element because of these pesky quantum dimensions unless it's integral. Maybe if, so conjecture, wildly optimistic conjecture, if your fusion category admits a regular element, so say it's integral, then you should be able to get a type 2 back. So good question. Thank you. Yeah, just change. There's something special about X, with the exception of if you induce it to the center and take end of it, that is the true algebra. That's one really good reason to use X. Okay, so that is the story from 2307. Now I want to move to 2506. This is stuff that appeared last week. Now I can finally go back to my first board. What we're going to do now is I kind of erase that physical boundary. Get rid of that physical boundary. We're back to the beginning.
Since we are
What's up?
at the boundary, can we say something about gapping or the gap nature of the edge states? Or
Right, so actually, states on this boundary algebra give states on the bulk
yeah,
that actually restrict to the ground state away from the bulk, or away from the boundary. Because of the existence of this quantum channel, you just extend that state via this quantum channel, and so it gives you a state-based approach to boundaries. And in this paper, we actually give a definition of what is topological boundary in terms of so-called Lagrangian algebra objects, these W-star algebra objects, and modular categories. And this has been explored further in Corey's recent paper from this week. And that has to do all about like sim TFT and boundary quantum fusion spin chains and everything. It's very interesting, very exciting. So Yeah, if you like SimTFT and you like operator algebras. Shameless plug for Quartz and Paper. All right, so now I want to bring in, just to make things confusing, a topological boundary. So we have so many boundaries. I don't know if we should call this the boundary algebra, but we did. And okay, what I'm going to do is make a topological boundary now. Topological boundary is going to be in blue for some reason, just a color I haven't used yet. So I'm bringing the topological boundary. So now I have a lattice with a boundary. Okay, so there's nothing over here, but it's still infinite in 3 directions if you're on the plane. If you're in 3 dimensions, it means I took a 2-dimensional slice and chopped it off there, but it's a topological boundary. A topological gap boundary is now in my system. Okay, so that's the way you should be thinking of it. I still have this whole thing of net of algebras. This idea hasn't changed. This abstract quantum spin system hasn't changed. No difference here. So now we need to talk about the local topological order axioms in the presence of a topological boundary. And I'm pleased to say not much changes there. So boundary LTO1, how does it have to change? Well, I have my topological boundary here. I have lambda here, delta here. And so if lambda is, again, completely surrounded, but up to the topological boundary by delta, then p delta and lambda p delta is again just the scalars times p delta. Okay, so again, this is this distance s on all the other sides. I just ignore the topological boundary from the whole idea of surrounding or not surrounding. I just get to ignore it because it's topological. Okay? I still have quantum error correction in the presence of the topological boundary. Okay. And then boundary LTO2. Now, then I have my topological boundary. I've got my lambda, but now delta is again going to share one side. And that side is here. And that's I. If lambda is now, I have this other symbol, it's contained, but not strictly contained. Then, again, I have a boundary algebra, maybe B partial I, supported near I. Again, independent of lambda and delta, beyond the fact that lambda and delta give you this, I can make lambda much bigger and then delta much bigger, as long as, sorry, I shouldn't, lambda could be going this way, and then delta would be huge, as long as it has that same I as the intersection here. Didn't matter. Such that, again, if I compress, now get, it's the same thing. You just basically ignore the topological boundary and write down the same axiom. All right, cool. Good job, David.
Check that. This topological boundary is classified fusion category, something like.
Let's do it for Levin-Wen.
Yeah.
We're going to do that example right now. Other questions before I do that?
Yeah, it looks like you're assuming the 4 rotation symmetry. It doesn't matter where you put this corner or the bottom, left, top.
Yeah. So again, the point is it didn't matter where I did it. I'm assuming that I have but here, you should be careful. Yeah, if you could do it here, that would be fine too. But here we want this interval here to be the topological boundary at the end. Yeah. So near I should be touching the topological boundary. Thank you. So it should look in the picture, but it could be on the top or the bottom. That's just basically choosing the category or its opposite, or the algebra or its opposite algebra. Okay. So that's a Z-mod 2 torso convention, which I'm happy to align. We have a notion of boundary DHR bimodule. And these boundary DHR bimodules now, these have FGP bases localized in any large enough interval meeting the topological boundary. So that interval has to meet the topological boundary, but now I can localize near the boundary. The warning is, this is no longer a braided tensor category. It may not admit a braiding. It'll be a category. It'll be a tensor category because it's a full subcategory of bimodules for its algebra. But it may not be braided. So let's do an example where it's clearly not braided Levin-Wen with a topological boundary. So here I've got C, I've got X there. What I'm going to do is I'm just going to add a topological boundary here in this way. I have a different Hilbert space along this part here. This is now equal to in a module category. So M is some module category for C from, I guess I'll choose W to W acted on by X, where W is the direct sum over the simple of M. So here I'm always thinking about reading it from bottom left to top right. That's kind of how I implicitly am doing that. Read that. That's a picture. Those trivalent vertices coming from M. That's the Hilbert space. And in order to really do this, in order to make this a Hilbert space, I need to pick what's called a module trace. And you have to be careful about your choice of module trace. And all of that is to make the subfactor theory, first to make it well defined, and second to make the subfactor theory in what I'm about to say go through. So you have to be careful here. Luckily, we know subfactors and it all works.
So what is M?
M is a module category for C. So it's a right C module category.
It's extracted from something or just
This is a Levin-Wen model. So now I'm going to pick a type com. Well, M is a unitary module category. But I want it to be a right module category.
So M could be C, that's the one.
M could be C, absolutely. That's like the
That's like,
Dirichlet now, right? Did I get it right?
Yes. But is there data in your boundary LTO one that from which you derive M?
No, M goes into the model. This is a model with topological boundary. And then given the model, it satisfies LTO1 if this is true. So this is a model that's built from M and C. And the theorem is it satisfies, so the theorem is this satisfies boundary LTO1 and 2. That's a theorem.
But the M goes into defining the algebras.
That's right.
Agents that contain.
That's right.
Okay.
So I've got some abstract quantum, it is a quantum spin system. It's just that the things on the topological boundary, the Hilbert spaces here are different than the Hilbert spaces everywhere else. That's why they're colored in a different color. The local C-star algebras are different based on whether you're here or here. Over the simples, pi naught is the new way to talk about irreducibles. Your category.
And the other symbol is
M.
and the other one,
This right?
no. Bounded by now.
M.
So
Strict M.
M is in pi naught of N.
And little m is in pi naught of N. So little m is a simple. I'm summing over the simples in my module category.
So the one is little m, the other one is capital M.
This is little m, that's a big script m. Script m is the
Okay.
module category, little m is a simple in the module category.
Perfect.
So great, we're doing okay here. Now I have to tell you what the boundary algebra is. So again, now I'm going to make a physical cut in the presence of my topological boundary. Okay, so I have my physical boundary that I put in, and then this allows me now to get this boundary algebra by taking this cut. And then the theorem is, so I look at B of I, in this case, it's NC of x to the I if I intersect the topological boundary. It's empty, but if it's not empty, then I'm going to get n in m of this W acted on by x to the I minus 1 terms if I intersect the topological boundary. It's not empty. So it's what you would expect. If I'm away from the boundary, I just get this fusion spin chain stuff. If I'm near the boundary, I now get stuff in the module category. So I would call this the fusion module spin chain. Okay. Fusion module spin chain. For C and I guess CX and W. Okay. And everything here is like a strong generator, so everything, all the theorems work nicely. So what happens is that the boundary THR, in this case, is equivalent to what you think it is. The dual category. Okay, so this is describing the topological boundary excitations. Okay, so we're getting the boundary topological order from the boundary DHR bimodules, as you would expect. That's what makes the whole theory go nicely. All right. Given that I only have 5 minutes left, I want to say something about Walker-Wang. I want to go up a dimension, which was the whole point of doing this in the first place, was to attack the Walker-Wang stuff. But I have 5 minutes to say something interesting about Walker-Wang. So let's do that. Here, this is where things get kind of complicated. First of all, I'm not going to. What my local Hilbert space now and everything, this is 3D. I'm not going to draw it beyond just the local Hilbert space now looks like this, and you can again resolve it. Okay, but the idea is I have this is now based on a braided fusion category B, and now I need a new name for the object. I'm going to call the object Y. That goes to each one of these. My Hilbert space is n in B of y to the third. Okay, where y is again the direct sum over the simples of B. Okay, so that's what I get for my local Hilbert space. Again, you have AL terms. These glue edges. You have BP terms. For all motets. There's no cube terms, so the Hamiltonian is basically built from that. Again, we're not doing Hamiltonian stuff, just doing the projections. The local projections are built entirely from these interactions. So it gives me these P lambdas now, where lambda is a three-dimensional rectangle now. Okay. So at this point, all bets are off about what I erase because there's 5 minutes left. Just go crazy, erase all the things. Here we go. So this is going to satisfy LTO1, LTO2. Great. The boundary algebra now is actually quite interesting. B is a two-dimensional net of algebras. Okay, the idea is that, and you're using various game module methods. I guess I could have gone back to that board. Would have saved me 30 seconds. The idea now is I look at this and I assign y to every dot here. And because B is braided, it makes sense that if I pick some rectangle R here, I can talk about an object called y to the tensor R in B. And you can say it's precisely using operads. The idea is if I pick objects from my braided category and I put them some places on the plane, taking a tensor product over those makes sense. Okay, that's a thing that makes sense. And therefore, here, the algebra associated to this rectangle is end in B, y to the tensor R. And so this is what I would call the braided fusion spin chain. Braided fusion spin system, something like this. And an aside that perhaps is interesting is the code algebras here are type 1. So they're finite direct sums of type 1 factors. Here, the super selection category is equivalent to B. So that's something that's worth studying in the future. We have an equivalence of categories. We expect it's an equivalence of braided fusion categories, but then you have to work through the fusion and the braiding of the full super selection theory. And it's kind of beside the point of this paper. And so we didn't do that in the paper, but surely something we're gonna do in the future. We expect that to work just fine. Okay, so we've got this braided diffusion spin system. This is the boundary algebra of the Walker-Wang model. You can do the Walker-Wang in the presence of a topological boundary. So in the presence of a topological boundary, how would that look? Well, it means that you would look something like this. Everything is like a 3D lattice, but then I'm chopping it on one side here, and when I chop it on that side, I take things from a different kind of module category. I pick now a module category for B, but that module category is a two-dimensional thing. It's going to be a fusion module category. So here, I pick X, which is going to be a unitary fusion category with a braided central functor. So it's going to go from B to set of X, down to X, of phi, that's phi z, that's the forgetful functor. And so that's what allows you to hook up this idea of this braided central functor is exactly the data you need to hook up a 2D Levin-Wen to the 3D Walker-Wang. Okay, so you put this in there, you take a physical cut, and then in this case, I just want to say the punchline because that's actually the boundary DHR. Oh, yeah, said they didn't say what we don't. Okay, in this case, the boundary DHR bimodules of this B with boundary is actually equivalent to the enriched center of X. Okay, so this is the stuff that commutes with B. This is B time inside of X, as you would expect. So it's actually giving you the boundary topological order, and that I've studied in previous papers with Fiona Burnell, Corey Jones, Peter Houston, and then with my own team at OSU. And then you can use this to get at the actual DHR bimodules for the Walker-Wang, and the idea is you enrich B in B tensor B op, you do a folding trick. So you do all sorts of folding tricks, and it'll tell you that the DHR bimodules up here, of B up here for just the Walker-Wang is Z2 of B, Muger center, as expected. So you're getting at the point defects here in this way from the DHR bimodules. So to do, find an operator algebra way using some kind of thing like this to get at the whole fusion tree category. Or quantum system here in 3 dimensions. I'll end there. Thank you very much.